Hello, I am Jacob, and today I am here with Jacob, Nick, and Kevin. And today we will be talking about functions. So, what is a function? A function is simply a mathematical statement that associates each input in its domain to exactly one output following a set of rules that make up the function. For example, function f of x equals x for all real numbers is a function, as each x in this function has a unique output, that being x. So it would look something like this, or whatever. So now that we've gone over basically what a function is, let's talk about a couple of useful functions we can have and the implications of those functions. The first such function is an injection. Now a function is one-to-one or injective if every element in the range is associated to exactly one element in the domain. For example, let's say the domain of function f of x is the numbers 1, 2, 3. Okay? And let's let the codomain of x be the numbers a, b, c, and d. So we write that out. A, b, c, d. Now suppose that 1 for this function f of x, whatever it is, for this function, 1 maps to D, 2 maps to B, and 3 maps to A. Now, as you can see, each element in our function here maps to exactly one other element in the domain. One other unique element in the domain, and so therefore this function is injective. And now the next type of function we'll talk about is a surjection. A function is surjective, or let me just write this out here, it's also called onto. It's surjective or onto if every element in the codomain has an element in the domain that maps to it. For example, function f of x equals y, and let's say that x is all real numbers and y is all real numbers. Now, this function, and now let's take this function and let's say that y is this x cubed, perhaps, right? Now, this function is surjective because every number in y, count that, in y, has a number in x that will map to it, some unique number in x. Let's contrast that. Let's say that y was equal to x squared, right? Now that would not be surjective because, let's say y, we want to find the value of 4. Now that could be either equal to 2 squared or it could be equal to negative 2 squared. Right? So it could be surjective. However, let's say we had negative 4. Right? Now negative 4, there is no real number that maps to that. The only thing you'd have is 2i squared, which is not real. So, as we can see, this function is not a surjection. So, now finally, let's talk about a third such function called a bijection. A bijective function is one that is both surjective and injective. Bijective functions exhibit both the qualities outlined earlier, so they're both one-to-one and onto. Now if we go back to our original example, the function f of x equals y, now this is a bijective, okay? It is one-to-one because there's only ever going to be one value corresponding to one value, right? 1 equals 1. And it's onto because for every element in y, there's an element in x that corresponds to it. So, this is a good example of a bijection. It's both surjective and injective. Now, an important fact about bijective functions is that a function is bijective if and only if it is invertible. This means that there is a bijective function that maps the set x to the set y, then there also exists a function that maps the set y to the set x, such that each element in y input to the inverse function produces the element in x that would map to the input to the original function. Essentially what this is saying is that if something is a bijection, then we should have some f inverse of y equals x. It maps the same values together. So now we're going to do a review of everything we just talked about and try to visually show this because it can be somewhat tricky. Now let's first show a bijection. Let's imagine that here is our domain x, okay, and it has the elements 1, 2, 3, and 4. And then we have the codomain y, which has the elements d, b, c, and a. Now, it's a one-to-one, so we know that for every function in x, there's only one value in y that will map to it. So let's do it like this. This is also bijective because for every element in y, this is also surjective because for every element in y, there's a corresponding value in x that maps to it. However, now let's go over the injective. It could be injective but not surjective. So let's imagine we have our x and it has the values 1, 2, and 3. And then we have our codomain y, which again has our a, b, c, d. Now let's say this is injective, so for every element in x, there's one element in y that corresponds to it. However, if you look at this little drawing, you'll see that it is not surjective, because there is a value in y that is not mapped to with x. Alright? Now, let's take a look at a function that is surjective but not injective. So let's see our codomain here, x, following the examples earlier. And I don't know why it's doing that weird thing at the top, just ignore it, please. We have our values 1, 2, 3, 4. You know the drill, right? You have our values a, b, c, and d. Now, let's imagine it has this sort of correspondence. The function produces something like, hang on, I got this. This. Okay? Now, as you can see, it is a surjective because for every element in y, there's an element in x corresponding to it. However, it is not injective because as you see, for the value c, there are two, count them, two corresponding x values. Finally, let's look at a function that is not injective or surjective. So let's just imagine this. Okay? Let's say it goes like so, and then maybe like this. Now, the first thing you'll notice, it is not injective, it is not one-to-one, because both 1 and 2 for the domain of x are equal to b. It is not a surjection because there are still values in y that are not mapped to with x. So, this covers what you should need to know about functions. Thank you for your time.